And this is lesson 7.3, stoichiometric calculations with moles, grams, and particles. So in our last lesson, we talked about stoichiometric calculation with moles and grams only. Today we're going to add in the particles part of that. And remember that those particles can either be atoms, molecules, or formula units, depending on what you are working with. And just as a review, we discussed this last time, but the two stoichiometry problem rules is that first you are going to need a balanced chemical equation, and then in order to convert from one compound to another, you must switch up moles and use the mole-to-mole ratio here in the center of our stoichiometry map. So, last class, we only talked about the bottom half of this. Today, we're going to talk about the top half as well. And unlike our mole unit, where there was only two pathways where you could either go straight down or straight up, there's going to be multiple pathways. We talked about this bottom pathway last time. So we talked about this pathway last class, and today we're going to talk about those particles. So we're going to talk about how we can go from particles of one chemical to particles of another chemical. We're also going to see that you can go from mass of one chemical to particles of another chemical, and particles of one chemical to mass of a different chemical. So there's a total of 4 different pathways that we can use here. So let me show you how to do this first problem. It says if you start with 51.36 grams of aluminum, how many molecules of hydrogen gas do you produce? We're always going to start with that number and unit that we're given in the problem. So the 51.36 grams of aluminum. And wherever it has this question, how many, or calculate, or what is the number, that's going to indicate what we want to find. So we want to find molecules of hydrogen. So we're going to start with 51.36 grams of aluminum. And I'm going to flip back to our stoich map. So we're starting here with our grams of aluminum, and we want to go up here to molecules of hydrogen. So the next step says that we need the molar mass. Well, the molar mass of a single atom by itself, no subscripts, is just going to be the average atomic mass. So that is 26.98 grams of aluminum. And remember, this is always the mass of 1 mole of that substance. So we're going to put that on the top. Flip back here. So we have gone from here to here. So we've done that step. So the next step says that we need our mole ratio to convert from moles of one chemical to moles of another. So in our chemical equation, we have 2 moles of aluminum, and we want to go to hydrogen, so we have 3 moles of hydrogen. If we stopped at this point, we would end up with moles of hydrogen, but we don't want that. So now we've gone through this step. And so since we want molecules, we're going to take this last leg of this pathway and go up here. So we're going to have 6.02 times 10 to the 23rd particles, and in this case, those particles are going to be molecules and molecules of hydrogen over 1 mole. So 6.02 times 10 to the 23rd molecules of hydrogen. and that's going to be over 1 mole of hydrogen. If we take a look back here, grams of aluminum cancel, moles of aluminum cancel, moles of hydrogen cancel. We're going to be left with molecules of hydrogen. So we're going to take 51.36 times 3 times 6.02 times 10 to the 23rd. Then divide all of that by 26.98 times 2. And you should get 1.719 times 10 to the 24th molecules of hydrogen. Remember that when we're working with Avogadro's number, the 6.02 times 10 to the 23rd, you can put that into your calculator as 6.02 E. You should have a second key, and then the x minus 1 will give you that E on your screen, and then 23. At least that's the case for the calculators that we use in class that I know many of you have. If you have questions about how to use your calculator and you missed class, please come in and see me. I want to make sure that the calculator is not the issue for you in doing these calculations. Okay, let's take a look at this next one together. So we are asked how many grams of oxygen are needed to produce 1.98 times 10 to the 23rd molecules. Okay, so look at it. Look at what are you given? What do you want to find? Well, if you answered that 1.98 times 10 to the 23rd molecules of SO3 is what you're given, that is correct. And you want to find grams of oxygen. So we're going to start with 1.98 times 10 to the 23rd molecules of SO3. Take a look back. We're going to use that Stoich map again. We're here at molecules. So we need 1 mole over 6.02 times 10 to the 23rd molecules. And then we are going to need our mole to mole ratio to get away from moles. So in our chemical equation, we have 2 moles of SO3 and 1 mole of oxygen. And then grams of oxygen, we need to calculate the molar mass of oxygen, but we have more than one atom, so we're going to take oxygen's average atomic mass of 16, multiply that by 2 for our 2 atoms, and that's going to give us 32 grams per mole. So we're going to put 32 grams of oxygen on the top, 1 mole of oxygen on the bottom. Molecules of SO3 cancel, moles of SO3 cancel, moles of oxygen cancel, and grams of O2 are what we're left with. So we're going to take 1.98 times 10 to the 23rd, multiply that by 32, divide it by 6.02 times 10 to the 23rd times 2, and you should get 5.262 grams of oxygen. Okay. If you're not getting this answer, you need to recalculate it with your calculator. And here in our last problem, it says how many molecules of oxygen gas are needed to react with 8.64 moles of butane. That butane is the C4H10. Okay, so I want you to pause the video, take a look at this, try to set it up, and then come back and you can check your answer. Welcome back. We have 8.64 moles of butane. That's what we're given in this problem. And we want molecules of oxygen. So in this case, we are going to start here with our moles of C4H10, and we're going to go here to molecules of oxygen. So in our chemical equation, we have 2 moles of butane. We use that mole-to-mole ratio since we're starting with moles. And then we want to go to oxygen, so we have 13 moles of oxygen. But we want molecules, so in 1 mole of oxygen, we have 6.02 times 10 to the 23rd molecules of O2. Moles of C4H10 cancel, moles of O2 cancel. We're going to be left with molecules of O2. So we're going to take 8.64 times 13 times 6.02 times 10 to the 23rd, divide that by 2, and you should get 3.381 times 10 to the 25th molecules of O2 for your final answer. Okay. You need to work through practice H, the stoichiometric calculations. There's a total of 10 problems, so make sure you do that. Come by, ask me questions if you're stuck. Next class, you will have a homework quiz over the first 3 lessons. So all the stoichiometry calculations that we've done thus far will be problems on your quiz. Your book assignment for homework number 3 is page 376 through 377, numbers 14, 15, and 16, 14 through 16, and then page 393, number 60. Thanks for stopping by. Have a great day.